Hello, everybody. This is Debasis Mitra. Welcoming you to the seminar of the Sense, Collect, and Move Data Center in DSI. Welcome. We are very happy to have as our speaker today, Jawad Ghaderi, who's an associate professor in the electrical engineering department. And he'll be talking about work that is joint with Christos Sanikidis, one of his PhD students. And you see the title up there on the power randomization. I'll just say a few quick words about Jawad and then the webinar rules as they apply. And then Jawad can start. So Jawad got his master MSc from Waterloo in Canada in 2008. And then he went on to Urbana-Champaign, University of Illinois at Urbana-Champaign, where his advisor was Srikanth, and he got his PhD there in 2013. And he had an offer from us, but he chose to spend a year as a Simon postdoc fellow at the University of Texas in Austin. And then he came to Columbia and he's been here since 2014. There's one thing, he's got several awards, but I did want to highlight one of them because it directly relates to his talk today. He received the best, he and Christos received the best paper award from Infocom 2020. That's obviously a very prestigious award and with a very lot of competition. And the award was given for this paper that we are going to hear about today. So we're very fortunate to have Jawad talk about this prize-winning paper. A quick word about the webinar rules. This is a little different from a normal Zoom seminar. I think you're welcome to ask questions during the talk, but you have to raise your hand. And only then will Alexis give permission for you to speak, and Jawad can hear you and respond. And we'll follow the same procedure at the end. By the way, you can raise your hand or you can send in a question in the chat box. Either way will work, but then permission will have to come from Alexis on a one by one selected basis. So with that, I will hand off to Jawad.
Hi, everyone, and thank you, Debasis, for the kind introduction. I'm happy to give the talk today. So this is a joint work with my PhD student, Christos Sanikidis, and it's about this new class of scheduling algorithms, randomized algorithms for scheduling deadline constraint packets in wireless networks. So, of course, there's been a lot of work. There is all literature on the scheduling algorithm and theory of scheduling in general. But we are witnessing this integration of sensing, communication, and computation, and it's creating all these new applications such as Internet of Things, vehicular networks, edge computing, and all these new applications that requires new schedulers because the resource allocations to satisfy the requirements of this type of application is even more complicated. And usually, you cannot just use the traditional scheduling algorithm to satisfy the requirement of these new applications. So, as I mentioned, in the context of wireless networks, of course, there are traditional scheduling algorithms, which mostly focus on long-term throughput. But in many of these emerging applications that I mentioned, not only you're interested in long-term throughput, but you want to also guarantee that packets are delivered within some specific deadlines, okay? So in these applications, deadline guarantees could be more important than just long-term throughput. In many of these applications, if packets are not received within their deadlines, they do not have that much value, or they have no value and are discarded by the application. As an example, if I have a network like that, right, and then you want to transmit this red packet over this link, you might have a deadline associated with this packet. And if you don't, for example, if you transmit this packet and it takes 50 milliseconds, maybe this is acceptable for this packet, for the red packet. But if I'm transmitting the blue packet, if suppose your time takes 100 milliseconds to deliver the packet over this link, it might be more than the deadline, which is satisfactory for the blue packet, right? So you could have similar situation even in different type of networks, distributed network or centralized networks. So in this talk, I want to design scheduling algorithms that can provide guarantees on delivery of these packets within their deadlines. So packets could have different deadlines, and we want to guarantee that what fraction of these packets we could deliver within their deadlines. So as I mentioned, we're dealing with packets that are arriving over time, and they have different deadlines. Just for mathematical purpose, we just want to consider, a mathematical model for this. So I'm going to assume that packet arrives and the deadlines are generated according to some unknown Markov chain. Okay, so as an example, if I consider, a network here, I have two links, right? The red link and the green link, and you could have different, traffic patterns for this network. So I could have, for example, if I look at here, the pattern A, here I have one packet. So here at this time, a packet with deadline 2 is arriving to green link. So what is the meaning of this? That the deadline is 2. That means I have 2 time slots to transmit this packet. So here at any time, in this example, I can transmit 1 packet at every time slot. So I have to select, should I transmit the green packet or should I transmit the yellow packet? So here, for example, if my pattern is A here, what that means is that I have a packet with deadline 2 arriving at the green link and a packet with deadline 1 arriving at the yellow link. I might have a different pattern. For example, here next time, maybe a packet with deadline 1 is arriving at link 2 and a packet with deadline 2 is arriving at link 1. Maybe you could have a different pattern that, a set of packets with different deadlines arrive at the green link and a set of packets with different deadlines arrive at the yellow link. So the important thing here is that I'm not assuming anything about the structure of this Markov chain. So here, you consider a general network, and then at any time, so here XLD is the set of packets with deadline D that arrives at link L in my network. So I have this network-wide Markov chain. All I'm assuming is that the deadlines are, they are bounded by some constant D max, but they could have this whole range. And then, you could have very complicated transitions between different states of this Markov chain. Okay, so for example, here in this example, you could have a Markov chain like this that you transition between different traffic patterns, right? Again, the important thing here is that I'm not assuming anything. So I don't know the structure or the transition probabilities of this Markov chain. Right? All I'm assuming that there is this unknown Markov chain that generates the packets and their deadlines over time. Okay, so because I'm talking about wireless networks, I have to also explain how do I model interference in wireless networks. So at the beginning of the talk, I'm going to consider a very standard model, which is based on what people call interference graph or complete graph. It's a very standard model. So for people which are not familiar with this model, so here the nodes of this graph are my communication links, and I put an edge between 2 links here if they interfere with each other. So you cannot transmit packets simultaneously, for example, over link 1 and link 2 in this network. So this is captured by this graph, which I call interference graph. For example, on the right, I have what I call a collocated network when all the links are interfering with each other. It's a complete graph. So here at any time, you have to select only one of the links for packet transmission because everything is interfering. For example, you might select link 1, and then you transmit 1 packet from link 1. On the left, you could have a general network, for example, and here, you could have more than 1 link activated at any time. So here my schedule at this time, for example, could be link 1, 3, and 5. Why? Because they do not share any edge. There is no edge between links 1, 3, and 5. Okay. So at any time, I have to select, my schedule is the set of links of the interference graph that they do not share any edge. And of course, these links, they should have unexpired packets in their buffers. Okay, so every link here has a buffer that contains its unexpired packets and their remaining deadlines. Okay, so this is my network model. So as I mentioned, this is a very stylized model of wireless networks. If I have time towards the end of the talk, we'll see that we could even incorporate fade into this model. So here, what I'm assuming here is that if there is no interference from my neighbors, and if I'm transmitting a packet over that link, that packet is 100% successful. But in reality, in wireless networks, the links are unreliable due to fading, for example. We could add those, unreliable links to this model as well. If I have time towards the end of the talk, I'm going to talk about that. But for now, let's focus on this. All the algorithms that I'm going to talk about also extend to that more complicated model. So what is the performance metric? Our performance metric is delivery ratio. So it's kind of your quality of service requirement. So delivery ratio is the fraction of packets of each link that are delivered to their destinations within their deadlines, right? So we measure over time as a result of your algorithm, what is the delivery ratio that you provide to different links. So what is our goal? Given an unknown traffic Markov chain that generates the arrivals and deadlines, and a quality of service requirement, a delivery ratio requirement vector P. So here PL is your delivery ratio requirement for link L. We want to guarantee that we can achieve at least this delivery ratio requirements. Okay, so that is our goal. Now, if you give me any scheduling policy new that you consider, of course, there is a set of achievable delivery ratios which are achievable by that policy mu, which I denote this by the capital lambda of mu, is the set of all the delivery ratio vectors which are achievable by mu. And then if you consider the union of this set over all the possible scheduling policies that you could consider, this is what I denote by this capital lambda, and this is what I call real-time capacity region of network. Okay, so it's the set of all the delivery ratio vectors that could be potentially supported by some scheduling policy. So that is my real-time capacity region. And I'm interested in designing online algorithms. So we're going to define the efficiency ratio of an online scheduling algorithm to be in terms of the fraction of the real-time capacity region that my algorithm can achieve. And I denote that by gamma star of that algorithm, which is the fraction of the real-time capacity region that the algorithm can achieve. So these are all just definitions that I'm making. Another useful quantity, so before I talked about our randomized algorithms, I'm going to also use this definition. So what is deficit Q? Essentially, deficit is a counter. You just measure how many packets you have to successfully transmit from a link within its deadline to satisfy its delivery ratio requirement, right? It's just a deficit, how much you owe to that link. So it evolves like this. So deficit of link L at time t+1 would be the previous deficit, plus I'm going to increase every time you have packet arrival to link L, I'm going to increase this deficit by PL on average. So you could exactly increase it by PL. So remember, PL was the delivery ratio requirement for link L. I'm going to increase the deficit. You could increase it by PL exactly, or for example, you could toss a coin. If it's 1, then if it's you could increase it by 1 with probability PL, or you don't increase it, right? So you just increase this by PL on average. And every time that you have a packet departure from link L within its deadline, I'm going to reduce the deficit by 1. Okay, so it's just a familiar dynamics for a queue. So every link here in my network has a buffer that contains unexpired packets and has a deficit counter, right? That measures how much, essentially timely packet transmission you owe to that link. So what we want now, if I make sure that over time, these deficit counters are stable, of course, the necessary condition for that is that the delivery ratio requirement, the delivery ratio that you provide to every link has to satisfy the requirement PL. Otherwise, this counter will go to infinity. Okay. Of course, we're not the only people who are looking at, scheduling deadline constraint packets. In the past 12 years, there's been a sequence of works. So it started with what we call frame-based traffic models. So in the frame-based traffic models, time is divided to frames. And then at the beginning of the frame, it's assumed that you know what packets and deadlines going to arrive during the frame. And then if I know this, of course, you know that the solution then for scheduling these packets in the frame would be a max weight or max deficit matching for matching the packets to time slot, or essentially a dynamic programming solution here would be optimal, right? Because I know everything here, I can solve that dynamic programming over the frame, and I find one schedule, and then whatever remains in the frame is going to be dropped by the end of the frame, and then the next thing happens at every frame, right? So of course, this type of algorithms, they are the only, they have this strong assumption based on this frame-based traffic model, and they are not causal because you're assuming the knowledge of future arrivals and deadlines. In this work, we want to design causal algorithms without making such assumptions. There is also work on greedy maximal schedulings, like largest deficit first. So essentially, in largest deficit first, you transmit the packet that has largest deficit. Okay, so I explained what deficit is. You transmit the packet that has the largest deficit. Then you remove the interfering links that interfere with this packet, and you repeat the same procedure. At the end, you end up with a greedy maximal schedule over the graph, and that's what LDF does. Performance of LDF has been analyzed also. If I consider IID traffic, when arrivals and deadlines are sampled from some distribution IID, then the efficiency ratio of LDF is bounded by is at least 1 over 1 plus beta. I'm going to explain what beta is. And if you consider Markovian traffic, the efficiency ratio of LDF would be less than 1 over 1 plus the square root of beta. So beta here is interference degree of the graph, which is the maximum number of links that can be scheduled if you consider any link and its neighbors. So for example, if you consider this a small network here, this node here has 3 neighbors here. So my beta is 3 here if I consider this network, because I can activate 3 links simultaneously at most. So my beta is 3 here, okay? So this is the performance of LDF that has been analyzed in this paper. So let's see an example how LDF works. So let's consider just 2 links. So I could just consider a network with 2 links, links 1 and 2, which are interfering with each other. So you could only transmit from link 1 or link 2. At the beginning, deficits are 0. And suppose these are the delivery ratio requirements. So P1 is slightly greater than 50%, and P2 is slightly greater than the delivery ratio requirement. P2 is slightly greater than P1. Okay, so you could choose any numbers that satisfy this requirement. And let's say you have a traffic, you have a Markov chain like this. So you're alternating between 2 traffic patterns here. In traffic pattern A, this packet arrived to link 2, this packet arrived to link 1. The next time, this packet with deadline 1 arrived to link 2, and a packet with deadline 2 arrives to link 1. Okay, I'm alternating between these. And let's see what happens if I use a greedy policy. So packets arrive. So the deficit is gonna go up, right? Deficit of link 1 gonna go up by P1. Deficit of link 2 gonna go up by P2. Of course, W2, deficit of link 2 is greater than P1. So LDF gonna transmit the packet from link 2. Okay. So then what would happen if you transmit this packet in the first time slot? Then you cannot transmit. You don't have time left to transmit the yellow packet, right? So this packet is successfully transmitted. This packet is deadline expires, so it gets dropped. Now the deficits are updated as a result of this packet departure that happened. Next time you go to the next pattern. These packets arrive. Deficits go up. Now here, deficit of link 1 is greater than link 2. LDF is going to select link 1 for packet transmission, right? So the yellow packet is going to depart in the first time slot, and again you have to drop the green packet, right? Because its deadline expires. And you will see that the same thing happens as you go through this Markov chain. You will see that essentially, if you apply LDF here, 50% of the packets from every link will be dropped. But of course, it's trivial that if I know what the traffic look like here, you could transmit all of them, because here in the first time slot, I should actually transmit this yellow packet. Then I have 1 time slot left to transmit the green packet, and so on and so forth. So if I consider optimal, you could transmit all the packets within the deadlines. But if I use this greedy scheduling policy, or even if you do what people call max weight, which is equivalent to LDF in this example, you could only transmit half of the packets. Right? So this is an example that shows that LDF cannot give you more than 50% of the real-time capacity region. Again, there's been this third line of work on worst-case approximation algorithms. So this work focuses on single link buffer management with fixed packet weights. You will see there is a whole class of works on worst-case approximation algorithms such as maximum weight greedy, different versions of earliest deadline first, that I'm not going to go through the details of that, and also randomized algorithms when you randomize over the packets pending in the buffer. So what I'm going to do in our work, after now talking about all these prior works, of course, in our work, we're focusing on a wireless network. So we have multiple links, and they have, they're subject to interference graph. And of course, our deficits are time varying, right? Because our system is stochastic. But I'm going to also use some of the ideas, some of the amortized analysis technique from randomized algorithms to our stochastic setting and for our wireless network model. Okay. So after talking about all this prior work, now it's time to talk about our algorithm, our randomized algorithm. First, I'm going to explain the algorithm for collocated networks, and then I'm going to explain the extension to general graphs. Okay. So let's consider this figure that I have here. So on the x-axis, I have the deadline of the remaining deadline of packets in my network, and on the y-axis, I have the deficit of their corresponding links. So if I, for example, look at this row, these are the packets of link 3, and these are their deadlines, right? So every row corresponds to packets of one link. The first thing that we're going to do, we only consider for potential transmission, we only consider the earliest deadline packet of every link. Okay. So if I do that, then you could get rid of the rest of the packets from this picture, because you only need to consider the earliest deadline packet of every link. And then we define a domination relationship between two links. So I say link I is dominated by link J if link J has higher deficits and its earliest deadline packet has a smaller deadline than link I. So if this condition holds, in some sense, link J has higher priority, is more urgent, right? Has higher deficit and has a smaller deadline. So based on this domination relationship, then you would see which links are dominating each other. So if I look at this figure, for example, you will see, well, link 7 is dominating all the links that appear in this region. Link 3 is dominating all the links that appear in this region. Link 1 is dominating all the links that appear in this region, and so on and so forth. So I'm all interested in these corner points because these are the links that are not dominated by anything else. These are my non-dominated links. After I found them, I'm going to select one of them. How? I'm just going to randomize over them according to these probabilities. Okay, according to these probabilities. So the probabilities depends on the ratio of the successive non-dominated links that appear here, the ratio of their deficits. So for example, if you consider these numbers to be the deficit of these links here, you will start from this link and you assign 1 minus the deficit 100 over the next deficit of next link divided by the deficit of this probability to this. So you according to this formula, you just go, you look forward and you assign probabilities. Of course, you cannot go forever because the summation of probabilities cannot be greater than 1. You have to stop at some point. You truncate the probability, and then you assign 0 probability to the rest of the links that appear after that. Okay. So after we have this, we just randomize over them. We choose one of them according to this probability, and we transmit the earliest deadline packet of that link. Okay. So that's the algorithm if I consider collocated network. So of course, this region is time varying, right? Because as I mentioned, we have packet arrivals and departures and deficit change. So suppose right now the set of non-dominated links is this. Well, you suppose you randomize and you transmit this packet from this link. Now the deficit is going to change, right? The deficit of link 3 is going to go down. And now maybe the next time, the set of non-dominated links would be 7, 4, 1, 2. Again, you randomize over them. Maybe this time you select link 2. Right? And then you have a different picture. Maybe you even have arrivals to link 1. So the deficit of link 1 would go up. So next time slot, the set of non-dominated links would be 1 and 7. Again, you randomize. Okay, so at every time slot, this region is time varying. You have to find the set of non-dominated links and you randomize over them. to choose to transmit the earliest deadline packet of one of these. Okay, so that's the algorithm. So what is the performance here? We could show that the efficiency ratio of the algorithm I described in collocated networks is given by this expression, lower bounded by this expression. So K here is the number of links in the complete graph or collocated network. And of course, this is lower bounded by 1 minus 1 over E, right? As K go to infinity. So just to give you an idea about whether this result is good or not, remember that if I consider, for example, just a collocated network, right? And if you consider LDF, I just gave you an example that LDF cannot do better than 50%. The efficiency ratio of LDF is less than 50%, but here you could achieve 63% or 64% if you apply this randomized algorithm. So this is significantly better than just selecting the earliest deadline, just selecting the largest deficit packet for transmission at every time. All right. So you could extend this algorithm even to general interference graph. So the idea here is, again, essentially is that instead of randomizing over the set of non-dominated links, I'm going to randomize over the set of maximal schedules of the graph. So let's consider, for example, this a small network here, and let's consider the non-empty links here, links that have packet for transmission. So here, then what are the set of maximal schedules that I could have here? Well, here I could have, for example, 1, 4, 1, 5, 2, 5, right? So the gray nodes here are the nodes that are part of the maximal schedule. So here I have 3 possible maximal schedules that I can consider for this network. The question is that which maximal schedule should I select? So for each maximal schedule, I define a weight, which is the summation of the deficit of the links which are part of that maximal schedule. So for every maximal schedule has a weight here. And then I'm going to order these maximal schedules in the decreasing order of their weights. Okay. And then if I want to, for example, randomize over the first n maximal schedules, I choose one of them according to this probability. Okay. So here, W of Mi is the weight of that schedule. And there is a constant here that I call subharmonic constant. Essentially, if you consider the first n maximal schedule, suppose you want to randomize over the first n maximal schedule, this constant is given by this expression. So what is this? Essentially, if you ignore this -1 in the numerator, this is just harmonic average of the weight of the first n maximal schedule. So here I have n-1 instead of n. That's why I call it subharmonic constant. Okay. So which n should I choose? You use the largest n that gives a valid probability distribution. And then, I'm not going to go to the details of that. If I have all my maximal schedules, so of course in a general graph, the number of maximal schedules could be exponential. If you forget about that complexity, if you could order this, if I have the ordering, then of course you could find the largest n through a binary search. But for now, I'm going to ignore the complexity of ordering the maximal schedules of a graph. If I have time towards the end of the talk, I can talk about approximation schemes for that and how you could come up with low complexity versions of this algorithm. But if you consider the algorithm I just described here, that you randomize over the maximal schedules, then you could achieve this efficiency ratio. So the efficiency ratio of the algorithm is lower bounded by this expression here. So here, this cardinality is the number of maximal schedules or the number of independent sets of a graph. No matter what type of topology do you have, this is always lower bounded by at least 50%. Again, just to give you an idea of how good is this result, let's consider like a star topology here. So I have one green node at the middle, at the center, and I have K leaf nodes here. So here you have 2 options, right? You could I have only 2 schedules. I can either select the green link for packet transmission, or I can select all the blue links here. I have 2 maximal schedules. So here I can just randomize over just two schedules, right? According to the probabilities I gave you. So n here is 2. If you plug this here, you would see that the efficiency ratio of randomized algorithm is 2/3. But if you apply LDF here, you would see that the efficiency ratio, as I argued at the beginning, I talked about the prior result, is less than 1/√of k+1. So if you start increasing the size of this graph, the efficiency ratio of LDF will go to 0. But this randomized algorithm gives you 2/3 independent of k. So it's much better. Okay, so that's all the results that I have in terms of the algorithms and just the main results. What I'm going to do in the next 20 minutes, I'm going to talk a little bit about the ideas of how do we prove these things. And then if I have time left, I can talk a little bit about how can you incorporate more realistic wireless models into the interference graph that I talked about. So essentially the proof of something like this has different steps. The first part of the proof is based on construction of frames, random frame construction. So as I mentioned, we have this kind of a unknown Markov chain. So well, you suppose you start from some initialized state here. Okay, suppose the state A, and then you just look at the return times of this Markov chain to this state, and each of them is called cycle. I can put a bunch of cycles together and I can form frames. So frames are consist of the cycles, and I can make larger and larger frames by putting more and more cycles together. Okay, so I have these random frames, and then I define the gain of a policy. So if you give me any policy mu at any time, the gain of that policy is the summation of the deficit of the packets which are transmitted by that policy at that time. Okay, so that's the gain of that policy at that time. And then over large enough frames, I'm going to compare the gain of our randomized algorithm with non-causal policies over that frame. So what are these non-causal policies? These non-causal policies, they have complete knowledge of the traffic that is going to happen during the frame at the beginning of the frame. And whatever packet left in the buffer at the end of the frame, they're going to drop that. We could show that as the frame size go to infinity, okay, of course, the capacity region which is achieved, our real-time capacity region, would be, satisfy this requirement. As the frame size go to infinity, essentially this the real-time capacity region would coincide with the capacity region which is achieved by this kind of non-causal policies, frame-based non-causal policies I talked about as the frame size get large. So the next step is that. So I'm going to now analyze the gain of our randomized algorithm over this kind of random large frames. If I can show that this expression holds, so the expected gain of our randomized algorithm over the frame, okay, divided by the gain of optimal is at least rho, then your initial deficit gets larger and larger. So that's what I mean by that. If I can show this property, if I can show this relationship, then it follows from some standard Lyapunov argument that you could achieve a rho fraction of the real-time capacity. Okay, so if I can show this, then the rest is a standard. So I'm not going to talk about it. The non-trivial part is showing this, that okay, if I consider a frame here, you start from some initial state. So you have some initial buffer size, some initial buffers, some initial deficits, and some initial state for your traffic Markov chain. And then you look at this frame, and over the frame, I want to compare the gain of my algorithm with the gain of these non-causal policies over this algorithm, over this frame. Okay. So that's the non-trivial part. I'm going to talk a little bit about how do we do this gain comparison. So first, let me just talk a little bit about gain analysis in collocated networks. Then I explain how this gain analysis is done in general networks. So algorithm and optimal, if you consider effective optimal algorithm, they have to select one of the non-dominated links that I talked about. So again, remember this figure. So we know that we have to transmit one of these corner points, but we don't know which one, right? So that's why we randomize it. So to analyze this performance, let's look at the actions of our algorithm and optimal, and whenever they disagree, we're going to change the state of the optimal to make the state match, but we make sure this change is advantageous for optimal. So for example, let's say that our algorithm and optimal, they differ in link I and J, right? So let's focus on that too, these two links. And suppose optimal transmit packet J, but our randomized algorithm transmit packet I. So then this would be the buffer content of algorithm at the end of this time step, and this will be the buffer content of optimal at the end of this time step. So first we want to make the buffers the same. So what should we do? we're going to replace packet I in the buffer of optimal with packet J. If you do this, this is only beneficial for optimal. Why? Because this packet has larger deficit and has larger delay, so it's better. So now the buffers are the same, but the deficit of the links here and here, they differ by 1. We match the deficits, but to take care of the possible, actions that are possible transmissions from these links during the rest of the frame, to make sure that this change of deficit is advantageous for optimal, we're going to just give optimal some extra reward. Okay. So now the deficits are the same, the buffer content is the same, and then we can process, right? We make sure that this now all the states are identical, and whatever change we made for optimal was only advantageous for optimal. Let's look at this, the second case. Suppose here, optimal transmits I, but our algorithm transmits packet J. Okay, now the buffers are different, so what should we do? Well, here, we allow optimal to transmit packet J for free. Of course, it's better for optimal, it gets some extra reward. And we're going to inject packet I back to the buffer of optimal. Again, this is advantageous for optimal. Now the buffers are the same. We make the deficit of the links to match again, but they have to give some extra reward to optimal. And that extra reward is the length of the random frame. Okay. Now, once we have this, we could compute the expected reward or the expected gain of this modified optimal here. So this expectation here is with respect to the random actions taken by our algorithm. So of course, if optimal transmit packet I, it gets this reward or this gain. But whenever our algorithm transmits the packet that has lower weight or lower deficit than packet I, if you remember here, I allowed optimal to transmit these packets for free. So optimal also get this extra reward here. That's why I have this expression here. How about the average reward of our algorithm? Well, here just, these are the probabilities which are used by algorithm, just randomizing over them, right? So this is the expected reward of our algorithm. And then we could show that if what you want to do, you want to just look at the ratio of these two and make the ratio as large as possible. That's what you want to do. If you use the probabilities that I described for the algorithm, you could show that essentially that ratio is at least 1 minus 1 over E. How the gain analysis is done in general networks is very similar. Suppose optimal policy transmit this maximal schedule, but our randomized algorithm selected another maximal schedule MJ, which is different from MI. What should we do? Well, make the buffers the same. How? We allow mu to transmit additional packets that were here, not here. And also we insert packets that were in this schedule, but not in this schedule. We insert them back to the buffer of mu. Now, the buffers are the same, but we also need to make the deficit the same. Again, we do this by the same trick, by the extra compensation or extra reward trick that I talked about. And then we could start essentially bounding, as a result of what I mentioned here, the result of the change, you could bound the expected reward of the optimal and the expected reward of our algorithm. And then you could find, you want to find this randomization probabilities to make sure that this ratio is as large as possible, right? So in the optimal, you need to solve, ideally, if you want to get the optimal choice of probabilities, you have to solve this optimization. All we have shown in the paper, if you just use the closed form expression for the probabilities that I explained, when I talked about the algorithm, this optimization would be at least lower bounded bias. All right. So this was just a very high level ideas of how do we go about the proof of the results that I talked about. There are some simulation results here. I don't know how interesting are the simulations. Again, the purpose of this simulation is that you could show that if you consider different delivery ratios for the links in the network, the deficits for the links remain very, very small if I apply this randomized algorithm. But for example, if you use different versions of LDF, you will see that this deficit will start going to infinity, right? Because as I mentioned, LDF cannot support the delivery ratios which are supportable by this randomized algorithm. So the deficit will start going to infinity if you apply LDF for different versions of LDF. But the deficits are really small and stable under a randomized algorithm. And similar situation, even if you consider different graphs, different topologies, different Markov chains, and so on. Okay, so let me just summarize the first part, and then just for 5 minutes, I will talk about some possible extensions. So in summary, just a summary of what I talked about is, we could achieve a constant fraction of the real-time capacity region without solving any MDP Markov decision process, right? Because the optimal solution to this problem requires solving an MDP. You have suppose even you learn this Markov chain, right? As I mentioned, you're dealing with an unknown Markov chain. But suppose you learn this Markov chain, or this Markov chain, then you could model the problem as an MDP. But then finding the optimal action requires solving a kind of like a Bellman-Ford equation or dynamic programming equation, which that it would be super complex to find the optimal solution to this type of problems. So here, what we have shown here is that you could still get the fraction of the optimal capacity region without solving any MDP or knowing the Markov chain. So we could achieve 63% in collocated and 50% for any general interference graph. And I think this technique could be interesting. Like suppose you want to solve some MDP, and then you want to bound the performance of your algorithm compared to the optimal solution to this MDP. This technique of modifying the state as you go over time, step by step, and then bounding the performance might be useful for other problems as well. Okay, so just for 5 minutes, I can talk about, okay, can you make, as I mentioned, we talked about this interference or complete graph-based model for wireless networks. I assume that links are reliable if there is no interference, but in reality, we know we're dealing with wireless environment and nothing is reliable. We could add all these complications to the model. So here you could have a model like this. So here you have packets, that arriving over time with different deadlines. And then at any time, you have what I call a channel success probability. So here, for example, if I transmit this packet here at this time slot, the success probability is 2/3. If I transmit, for example, the yellow packet in this time slot, it's 100% successful. This packet could have different success probability at different times. So you could have even a fading or a kind of a link reliability probability process or a fading process over time. Okay, in conjunction with your arrival and deadline process. And the question is that how can I make these decisions? Now the problem is more complicated, right? Even if I transmit the packet at this time, there is no guarantee that that packet will go through within its deadline. So I might have to repeat several times according to those probabilities. So here you could extend everything again. I don't need to assume that I know the structure or the future packet success probabilities or channel success probabilities. I don't need to know that. I only assume that I know the current channel state information. That's the only thing that I assume. I don't know the future evolution. You could extend all these algorithms. I'm not going to go to the details, but all these algorithms can be extended to this model. You could still do randomization. You could find the probabilities carefully, and you could bound the performance of those. I talked about the high complexity of randomization for general graph because you need to find all the maximal schedules. You could come up with different versions of that. You could come up with color image randomization. That essentially here the idea is that look, instead of randomizing over all the maximal schedules, you could just randomize over a set of maximal schedules that cover the graph. You could randomize over that according to the probabilities and still get the fraction of the real-time capacity region. You could even come up with distributed algorithms or myopic randomization that the algorithm is totally distributed. So there are different versions of that. If you're interested, you could look at the papers. And yeah, let me just end the talk here. So we have done a lot of work essentially at the intersection of a stochastic network and combinatorial optimization. We're trying to essentially bridge the gap between these two this type of networks here, because as I mentioned, as you go through this emerging applications, problems are becoming more and more. You're dealing with the stochastic networks, but the problems are becoming more and more combinatorial. And when you look at the literature from a stochastic network, they cannot deal with this combinatorial problem. The question is that how can you essentially come up with an approach to unify these two types of optimizations? So I've been doing a lot of work at the intersection of these two types of networks. You could see a list of them here for different applications. And if you're interested, so The talk that I gave today was based on these two papers. You could, if you're interested, you could see the details of the analysis in these papers. Thank you very much.
Thank you, Jawad. Thank you very much for this most interesting paper. It's not easy paper, but certainly important one. Questions from the audience? Does someone have a question? I think if you raise your hand, we'll be able to see, and then Alexis will allow you to speak. This seems to be the protocol that for webinars that DSI uses. Does someone have a question? Well, let me just kick off a question and ask you, Jawad, very generally, almost philosophically, deadlines is a very deterministic phenomenon, right? You have it for traffic, for driverless cars, things which are, very time constrained, right? And very tight. Now, and randomization is, probabilistic, right? So when you come to apply this to real world scenarios, what are the issues that you run up against?
So one of the issues is that who's telling you what the deadlines are, right? So you have this package arriving. How can you infer the deadlines of packets? Of course, in future, you might assume that this package also carry the deadline information, right? But right now, if you look at the network, you have to infer the deadlines of packets somehow from the packets. Now, there are two ways of doing that. Either you look at the packet header information, and you could realize what type of applications those packets are generated from, and based on that, you could impose the deadlines of the packets, or the scheduler could itself just come up with some deadlines, right? Packets do not have to carry that deadlines necessarily. I don't know if I answered your question, Debasis. So this is one of the issues.
But let's see. Now, going down that hole a little bit deeper, if you have the two issues, like the implementation time, that the time required to make a decision, and the second one is the guarantees, right? Do you want to just say something about the nature of what you end up with for real world applications in these two?
So the first algorithm is very simple, right? You just need to essentially find, because, for example, you could, for the first algorithm, suppose you consider your Wi-Fi access point, right? And then you consider downlink, right? You have multiple devices, you have to make decisions that which packet should I transmit over my channel right now. So you could just that doesn't have that much, doesn't have a high complexity, because you could do everything centralized at your access point. You have the buffer of your queues at the access point. You could find the non-dominated packets and you randomize over them. And the complexity of that is just the complexity of just sorting an array. So if I have k users, the complexity would order k log k or something like that. So it's very efficient, right? So if I have the first algorithm is very efficient for collocated networks or a Wi-Fi type network. But the second algorithm is more complex, as I mentioned. Then you have a general network, right? Then the question is that, what type of architecture you should use to implement algorithms like that. As I mentioned, sometimes for a small networks, you could use some master-slave type of architecture to implement those algorithms for general graphs. But if the graph is really, really big and you have a lot of independent sets, then it's very complex to implement the generalized randomized algorithm. So I talked about, I briefly towards the end of the talk, I talked about some different versions of the algorithm that you lose a fraction of the grant that I gave you, but the complexity is much lower and you could do everything in polynomial time still.
And in the terms of guarantees, what do you,
So guarantee of the as I mentioned, the first algorithm, you could get the guarantee that I mentioned, you could achieve 63% of the optimal, and the complexity is really low, right? Almost polynomial. For the second algorithm, if you forget about the complexity, you could achieve something which depends on the number of independencies that you have. It's at least 50%, but it depends on the topology. But you lose. So if I have we gave up towards the end of the talk. I talked about different low complexity versions or distributed versions. Again, I can achieve some constant fraction, but you lose. You cannot. I cannot even achieve 50% if I go there. So if I want to give you like polynomial complexity or distributed versions of the algorithm with constant complexity, it depends on, for example, depends on the topology of the graph. For example, I can give you 1/1 plus delta. Then delta is the interference degree, the degree of the graph that I'm dealing with, but I can give you a totally distributed algorithm. Of course, now 1/1 plus delta could be, smaller than even 50%. So you lose the guarantee that I talked about, but I can, we have this whole class of algorithms. Depends on what type of complexity we can deal with.
So does someone else have a question? Anyone? Maybe one last question, if no one else, Jawad, what kind of acceptance have you got from people who are applying these in the quote unquote real world?
So this is like a very classical problem because this has been open for a long time, right? How do you come up with scheduling this package? As I mentioned, 10, 12 years ago that people started working on this problem, they had to make some assumptions on this type of problems to be able to solve them, right? So the question was that because the optimal solution without making an assumption requires solving an MDP, right? And then the question is that, okay, what do you do about that? So I think just the fact that we're able to make a progress towards solving a problem that has been for that time is
but when people start applying it, they run up against a whole set of new issues and all that. So I was just wondering what the history there is.
So I think there is.
We just have one question. Thank you, Professor, for this amazing presentation. How do you see the comparison between the reinforcement learning-based scheduling algorithm and randomized scheduling? I feel the RL-based algorithm doesn't put the randomization into the decision. Will the RL work even better when it can also utilize the power of randomization?
So that's a great work. That's a great question. So as I mentioned, we're dealing with an MDP. There are various ways of solving that MDP. Nowadays, people talk about reinforcement learning, right, or deep reinforcement learning. So actually, one of the projects I'm really interested in is that, look, we're investing so much time trying to come up with algorithms and proving guarantees on those. So actually, I gave this project to a master's student that worked with me. That, okay, suppose you train, you do reinforcement learning, right? Can you come up with an algorithm and compare the performance of those algorithms with the randomized algorithm that I just described here? Can reinforcement learning or deep reinforcement learning or anything like that beat the algorithms I talked about here? So that's a very interesting question. And I think even if you want to apply reinforcement learning, there are, you have to design your network to somehow capture the structure of the problem. So what do I mean by that? Here, I could have started with designing or training my reinforcement learning model, or based on, suppose you don't know anything about the structure of the problem, that even which packet should I transmit. But now, if I know some domination relationship, for example, in the first algorithm, I know I have to transmit one of the non-dominated things. So if I know that, now this is the structure of the problem, right? Can I capture that structure in my reinforcement learning rather than just doing a blind reinforcement learning? I think that would be really interesting. Or even for the second problem, right? So I think it doesn't mean that, okay, if you want to use reinforcement learning, you could just throw away all the algorithmic ideas. I think it would be very interesting to see if you could use your insight about the structure of this problem when you're talking about reinforcement learning and designing algorithms there. This is, of course, been a very high-level answer. Like, it wasn't very accurate.
Anyone else have a question? Thank you, Jawad. That was a very interesting.
Thank you very much, Debasis.
But this last connection with the initial learning was particularly interesting. But thank you very much.
Thank you.
No other questions. Thanks. That's great.
Thank you.
Bye.
Bye.